See here, this is the experiment number 10. We are going to determine the shatter and tumbler strength of given raw material. Given raw material, we are taking two raw materials. One is iron ore, other one is limestone. Both are in the size of -20 plus 10. So we are going to determine the tumbler strength and shatter strength of these two raw materials, iron ore and limestone. Actually, why we have to conduct this test? What is the importance of this test? Before charging into the raw material into the furnace, those material will be subjected to different operations. Starting from mining, we have to loading, unloading, transporting, screening, so many operations it will go through. When these materials are going from one process to other process, from one stage to other stage, what will happen? The material will be subjected to impact forces, means sudden load. The material may fall from certain height, so the material will be subjected to impact loading. The material may be subjected to shear force. Due to the shear, so the material will break, due to where it will generate fines. So before charging into the blast furnace, due to the lack of strength, it may generate fines. So we are checking the behavior of these raw materials. How the material of behavior of raw materials we are checking, whether it is having sufficient strength or not. If sufficient strength is there, then it will not generate fines. So that will give you a better raw material. Otherwise, if it is generating fines, so it will create a problem when you put in the blast furnace. So here, for checking that, we need the apparatus. So we have two setups are here. One is shatter strength setup, other is tumbler strength setup. Anyway, after this one, you will see practically, you will see the real equipment, and we are going to do this practical, so clearly you can understand. If you are seeing the diagram of the shatter strength, the equipment diagram, it is a mechanical structure. If you see, some framework is there. Mainly top, what we have open top, and we have the bottom here. Here open top is there, here bottom is there. Bottom is not a single plate. That bottom is divided into two plates, two halves. So when we open, one hinge will be there. That when we open the hinge, it will open these two plates, then material will fall. So initially, before loading, what we will close it with the help of the hinge, and the bottom will be closed. We will put the raw material into this steel box. After that, we will release this bottom, because this bottom is having two halves. When you open the hinge, that two plates will be separated, then material will fall down. So the distance between the actual bottom, we have the plate of thick steel plate, it is there. The distance between this thick steel plate and this one, from which the material is falling, is 2 meters. So from 2 meters height, we are falling the material. Means we are subjecting this in the raw material to impact force. Due to that impact force, what will happen? The material will break. Here for testing that, how we do the testing of this shatter strength of the raw material. The raw material generally will take 20 kg, but in the laboratory scale, we will take 5 kg raw material. So 5 kg of raw material, suppose like this raw material, you can see iron ore. 5 kg raw material, we will weigh it and put inside this drum. Before putting, we have to ensure that the bottom is closed. After that, we will open that hinge the material will fall from a height of 2 meters. One time it is done, again what we will do, again the same material will take it and put in the bin, again second time will drop, like that 4 times we have to do. After 4 times the same material will be collected, and after collecting the material what we have to do, by using the sieve, which sieve, plus 10 mm sieve, the input, the material what we put initially in the steel drum or steel box, that is of -20 plus 10 mm. Here what we have to see, what are the material that we collect from here after 4 drops, we will put here and we will screen it. When you screen this one plus 10 mm, what will happen? The above plus 10 mm material, above 10 mm material, that is plus 10, the material will get here, and below 10 mm it will pass here. So what are the material retained on 10 mm screen, that is plus 10 mm material, we will collect and we weigh this material. After weighing, the weight fraction, what is the weight fraction we got, divided by initial weight. Suppose we are taking 5 kg, that is the initial raw material weight, into 100, that will give the shatter strength. It is very simple. So this is about shatter strength. So in the tumbler strength, here 2 things are there. One is, here in shatter strength we observed only impact, but in the tumbler strength, here impact also there. Actually how it will do, it is just a drum, cylindrical drum is there, we will put the raw material and close the door. Inside the drum, what are the things are there? Some lifters are there. So when we rotate this drum, how much, what is the RPM required? How many revolutions we have to do for doing this tumbler strength? At least 200 revolutions and 25 RPM, 25 rotations per minute. If the motor is provided, then it will maintain that RPM, 25 RPM, 200 revolutions. We have to subject this material. So what will happen? The material will be rolled, it will subjected to the tumbler action. So here lifters are there. What the lifter will do? Through lifter, material will be lifted up to this height. The material, how it will be lifted? Due to the friction, it will be lifted, and after attaining this height, the material will fall down because of gravity. So while it is fall down, see here we can see the impact. Due to the impact, the material will become into the pieces. It will get fractured and disintegrate. And here you can see, due to the shear forces, the wear of that raw material will generate fines. That fines we can see here. So here we are seeing the 2 things. One is fracture of the material or disintegration of material due to the impact, and generation of the fine due to abrasion also. Here you can see. That's why this tumbler strength test will give 2 indexes. One is tumbler strength index and other one is abrasive index. Percentage of abrasive index also we can calculate, percentage of tumbler index also we can calculate. So for calculating the what we'll do, once we are putting the material and we'll complete the 200 revolutions at 25 RPM and we'll take out that material. So here we have to use 2 sieves. In case of shatter and strength, we have used only 1 sieve. Here we have to separate 2 weight fractions. Which weight? Once the material is taken from tumbler strength equipment, we will put the material on the above, on the 6.3 mm screen. So we have to consider 2 fractions. One thing, what is the material retained on the 6.3 mm, means plus 6.3, and what is the material passed through 0.5 mm screen, that is minus 0.5. So we have to take the weight fraction of the plus 6.3 and weight fraction of the minus 0.5 mm. The weight fraction of the weight fraction on the 6.3 mm screen divided by initial weight. Suppose 5 kg material we are taking minus 20 plus 10 mm into 100, multiplied by 100, it will give the tumbler index. and the weight fraction which is passed through the 0.5 mm stream. That weight fraction divided by initial weight of the sample and multiply 100 will give abrasion index. So as we discussed, shatter index, this is the formula. What is the weight fraction that is written on plus 10 on the screen divided by initial weight. 20 kg if you are taking, then 20 kg you will substitute. If you are taking 5 kg, 5 kg you will substitute. That is a plus 10 mm into 100. Like the tumbler index also, first sieve, the top sieve, bigger sieve, that weight of 6.3 mm plus 6.3 surviving in kg divided by 15 kg initial sample, that is a plus 10 mm into 100. For abrasion, that weight fraction of minus 0.5, the weight fraction that is passed through 0.5 mm stream is 0.5 mm. Sieve surviving in kg divided by 15 kg, that initial sample weight plus 10 mm into 100. But in our laboratory, we have taken the initial sample weight is, that is 5 kg. So in case of coke, because we are doing the shatter index, tumbler index, abrasion index of iron ore and limestone. Coke also we can do that one. For doing the coke, how we will calculate? There we are going to take 22.7 kilo. Suppose we want to do shatter index of this coke. What we'll do? We'll drop this 22.7 kg 4 times on steel plate for a height of 2 meters. So the surviving weight material we take, that is weight of plus 50 mm surviving in kg divided by initial weight of the coke is 22.72 into 100. That will be the shatter index, percentage of shatter index. So here two things we have to see. Here we are seeing plus 50 mm. Plus 50 mm C we are using it. For getting the accurate exact coke strength, if you want to get the accurate picture of this coke strength, we can use other screens also. If you report, then it will give a accurate picture. Instead of only using one screen 50 mm, 37, 25, 12 mm also you can use, then you will get a good picture of this coke strength. This is the experiment number 10. We want to determine the shatter and tumbler strength of the given raw material. In this experiment, we have two things are there. We have to find out two things. One is shatter index and tumbler index. We have separate equipment, separate setup is there for checking the shatter index and checking the tumbler index. So initially we are going to determine the shatter index of the two type of raw material. One is iron ore, other is limestone. So which material we are taking? So this is the iron ore, minus 20 plus 10 mm. Iron ore is there. How much we are taking? We are taking 5 kg. Generally we should take 20 kg for the experiment, but for laboratory purpose we don't have that much quantity, so we are taking 5 kg of this one, minus 20 plus 10 mm iron ore. And one more raw material using the blast furnace, that is limestone we are taking. This is also size of minus 20 plus 10 mm. This also we are taking 5 kg only. Instead of 20 kg we are taking 5 kg. 5 kg iron ore and 5 kg limestone. Setup of shatter index. Shatter means fall into, broken into pieces. Here what we are breaking? We are taking the iron ore. What we are checking? We are checking the shatter index. Shatter means it is the resistance of the material to become into fragments. We should have the, what we will do, we will fall this material from certain height, from this height, from 2 meter height. What we will do, we will make them fall. The material will be falling on the steel plate. Here we are seeing the arrangement. Here box is there. In this box, you can see inside top it is open. Top it is open. Bottom we have two halves are there. Bottom we have two halves. So material has to fall from this height. First we have to keep the material inside, then we will open these two doors. That arrangement I am explaining. This one is a simply one box. Top it is open. Bottom we have two halves like this. How it will be locked? It will be locked by this latch. Locking this latch. So now it is closed. Once it is closed, we will take that 5 kg material, suppose iron ore, we will keep in this box, and after that what we will do? We will open this door. Then from this height, 2 meter height, bottom what is there? It is of thick plate, a thick base plate. Okay, thick steel plate is there, in that it will fall. Means we are subjecting this material to impact. Free fall, when it is free falling, it is subjected to impact force. In that impact, it will break into pieces. So, how much metal will be retained? Once it is falling, what we will do? At least 4 times we have to do the experiment. We have to keep the material inside the box and make it fall. The material will fall. Some pieces plus 20 mm we are taking. Some will be broken into pieces. Some will be retained in the same size. So what are the size retained? That one plus 10 mm size retained. That weight fraction we have to take, because to find out the shatter index, what is the formula? We have this formula: shatter index, weight of the plus 10 mm surviving material in kg divided by 5 kg of the material. Initial sample weight is 5 kg, that is plus 10 mm into 100. So here initial raw material weight is 5 kg. After plus 10 mm we are taking, and that 5 kg material we are making it to fall, and we are subjecting it to impact force by putting this material into the setup. Then once the material is fall, I told already number of drop, 4 drops you have to see. 4 times we have to make it fall. After that what we will do? We will make it, we will do the screening. Once you screen, 10 mm sieve we will take. For that 10 mm sieve is there. So we will screen it. Whatever the material retained above the screen, that is plus 10 mm. That weight fraction we will take. That will be the numerator. Denominator will be the total initial weight. How much we are taking? 5 kg material we are taking. Multiplying by 100, it will give the percentage of shatter index. Means in this experiment, what we are going to do? We are subjecting this iron ore or limestone, whatever the raw material we are taking, we are subjecting to impact by freely falling. That freely falling material is falling on the base steel thick plate. So when it is falling, when it is subjected to impact loading, what will happen? It will break into fragments. So like that we repeat this experiment 4 times. Once after 4 times, what will we collect that material, and by using this screen plus 10 mm sieve is there, with the help of this sieve we will do the screening of that material. Whatever the material passing through this 10 mm, that will not take. Whatever the material retained on the screen, that is plus 10 mm, that weight we will take, we will put in the numerator, and in the denominator we will keep the initial weight of the sample which we have taken, that is 5 kg into 100, that will give the shatter index. This is a very simple experiment. This is about shatter index test. Material, what we have done, we have brought this drum down by this pulley arrangement. So now it is in this height. We are loading the raw material iron ore. Now it is right. Now we are going to open this one. Now we are going to open the first. So material is fallen on the steel plate. So we will collect this material. Again we will make it ready for next drop. Second time we are loading this iron ore. And open the door. Collecting material. Third time we are loading this material iron ore. Third time we are opening the door. This is the fourth time. Minus 20 plus 10 mm iron ore again. We are putting into this. And we are opening the door, the bottom door. So this time, after collecting the metal, we have to weigh the fraction, weight fraction. Because 4 drums are completed, now we take this weight fraction to calculate the shatter index, percentage of shatter index. So we are taking with the help of this 10 mm. Extractive material will now this is the material fraction, weight fraction retained on the 10 mm screen, means plus 10 mm. The total weight is now 4.85. This is the weight fraction obtained, that is of plus 10 mm. Now we are taking another raw material, minus 20
plus 10 mm limestone. Now we are opening this box, bottom we are opening for first drop down. We will open. So second time we are dropping the limestone, managed to get the split. So we are opening the bottom hinge. Third time we are putting the raw material into this box, limestone. And we are making them fall. The raw material is falling back. Last time, that is fourth time, we are putting the raw material limestone. And we are opening the door, bottom door. Completed this one. So, 4 drafts are already completed. So now we are collecting the material because we have to weigh this fraction like previously done for iron ore. Now we are doing the sieving of this material with 10 mm sieve. Minus 10 mm fraction is very less. Now we will take the weight of this plus 10 mm material limestone. Now we are taking the weight fraction of plus 10 mm limestone. Now the weight is 4.75. Now we can see the shatter test observations. First is iron ore. Its weight we have taken 5 kg initial weight. So after the test, the weight of the plus 10 mm is 4.85 for iron ore. So finally we got the shatter index percentage. W2 by W1 into 100 means 97% we got. So iron ore shatter index is 97%. In the same way we done for limestone also. Initial weight is 5 kilo and after the test plus 10 mm weight fraction is 4.75. The final shatter index percentage of limestone is 95%. This is the experiment number 10. We are determining the shatter and tumbler strength of the given raw material. Those two raw materials are iron ore and limestone. Previously we have done the shatter. index, percentage of shatter index we have calculated. Here in this segment we are going to determine the tumbler strength of the given raw material, means iron ore and limestone. Both we are taking of the same size, minus 20 plus 10 mm. The quantity we are taking, instead of 15 kg we are taking 5 kg because of laboratory purpose. We are taking the we don't have that much of material, that's why we are taking less quantity, 5 kg. Generally we can take 15 kg. So what are the equipment required? Tumbler test setup it is there, and balance is required to weigh the raw materials. And sieves, we need two sieves, one is 6.3 mm, other is 0.5 mm. Because why these two sieves are required? Because we have to calculate the two things, one is tumbler index and abrasive index. For calculating the tumbler index, we need the percentage of material weight fraction written on the 6.3 mm screen and divided by initial weight of the sample, that we are taking 5 kg, multiplied with 100, that will give the tumbler index. So one more sieve what we are taking, that is minus 0.5. Why it is required? Because we have to check the abrasion index, that the material which is passing through 0.5 mm sieve, that will be that weight fraction we are taking to calculate the abrasion index, divided by initial material, that 5 kg only we are taking, into 100. So procedure is, so here this is the setup. You can see the drum, it is there. In this drum we are going to put the raw material. Here if you are seeing, this is the diameter and this is the width, and here we are putting the material. So we have the provision to rotate this drum like this. Generally this exact setup, if you are seeing the dimensions, actual proposed dimension of the equipment will be diameter. Diameter is 1 meter, 1000 mm, and width will be 500 mm. And inside there will be lifters, because here we are checking what? We are checking the tumbler index. Tumbler index also like shatter index. It is the susceptibility of the raw material to break down into pieces because of the impact force. There we have created, where in tumbler, while calculating the shatter index, we have the material has fallen from certain height, 2 meter height. Here material, how it is falling? When we are putting the material inside the drum, inside the like steps, there will be a lifters will be there. That lifters what will do? That lifters will lift the material up to this height. Whenever it is reaching that much height, then the material will fall. When the material falling at certain height, it will be subjected to impact. Due to this impact, the material will be breakdown. So we are checking this susceptibility of the breakdown of this material under impact force. Why we are doing, because when we are loading, unloading, and we are transporting, the material will be subjected to this impact. Because of that, material disintegration will happen. That may break into pieces. So that's why we need to check whether this material should have that sufficient strength or not. It should not be broken into small pieces. Otherwise, you can't use the material. So this is the drum, but what we have to maintain? We have to maintain how many revolutions? 200 revolutions, and that is 25 rpm speed is required. If motor is set up with this, along with this drum, then it will maintain that rpm, 25 rpm, and here we are rotating 200 revolutions with this same rpm, 25 rpm. Initially we load that plus 10 mm, minus 20 plus 10 mm raw material one by one, and we will subject to this tumbling action, means rotating of the given measurements. Like 25 rpm we have to maintain, 200 revolutions we have to rotate. And after that, once the material is rotated certain rpm, that is 25 rpm, 200 revolution, when it is completed, we will take that material. Then we have to take the two screens. That is 6.3 screen. Here this is 0.5 mm screen. Then whatever the material, that is subjected to tumbler action, that material will collect and will put on the screen, and we have to see that what is the material weight fraction retained on the 6.3 mm. That fraction weight we have to put in the numerator of this tumbler index formula, and initial weight we know that is 5 kg into 100, you will get the tumbler index. For abrasion index, because this is the 0.5 mm scale, so 0.5 mm scale, through the weight of the material passed through this 0.5 mm scale, that will be the minus 0.5. That weight fraction which is passing through the 0.5 screen, that weight we have to keep in the numerator of this abrasion index percentage formula, then divided by initial weight what we are taking, that is 5 kg into 100 will give the abrasion index. Now we will start the practical. So 5 kg iron ore, we are taking this one, minus 20 plus 10. It is already weighed. We are putting into the drum. Closing the drum. Ready करें? Now we are subjecting to 200 revolutions. Now we are taking out the sample out.
after the tumbler test, initial material weight fraction we received. Now we are saving with this through help of two sieves. You can see 0.5 mm skin and this one is 6.3 mm. So we want to separate the plus 6.3 and minus 0.5 mm. Plus 6.3, what are the material written here, that will be separated here, and 0.5 the material passing through 0.5, that is minus 0.5 material will be collected in this tray. So these two fractions we need to calculate the abrasion index and tumbler index. Now we will weigh the two fractions, minus 0.5 and plus 6.3. This is the minus 0.5 mm fraction weight. In the 5 kg raw material limestone, we are going to check the tumbler index. Further, we are putting this material into this drum. After closing the door, we have to submit for 200 revolutions to calculate the tumbler index and abrasion index. So this is not a motorized setup, that's why you have to do manually only. So we start 200 revolutions. taking out the raw material after tumbling action. Maybe 9 is 0.5. 6.3. After tumbling reaction, these are the raw material, limestone. We are going to see this here. We need plus 6.3 fraction and minus 0.4 mm. This is minus 0.5 fraction weight, that is showing 25 grams. So this is the plus 6.3 plus 6.3 fraction weight. This is coming 4.87. So in the results, initially we will see the literature. Here in the literature what we have seen, iron source from Konkan, Mahamaya, Rajhara. From the 3 iron sources are there. So their values also we have shown, that shatter index percentage, tumbler index percentage, abrasion index percentage. If you clearly observe, Konkan is having 94 shatter index and tumbler index 81.2, abrasion 11.7. Here you can see we need the high values of shatter index and tumbler index, because these two indicate the resistance to impact. And here also we need less abrasion. We don't want generate more fines, otherwise it will create a problem when you charge in the blast furnace. So when you are seeing the 3 type of iron resources, Konkan it is having less abrasion index compared to Mahamaya and Rajhara, and more shatter and tumbler index. So it is, this Konkan is best among these 3, suitable for blast furnace to charge as a lumps. If you are seeing Mahamaya, it is in between, that is 91.3 shatter index, tumbler index 74.2, abrasion 50.3, means it is better than Rajhara, but it is near to Konkan. But Rajhara, when you are seeing, the shatter index strength is less, tumbler index also it is less compared to Konkan and Mahamaya, and reversely you can see abrasion index it is more, which is not required. So it is tendency to generate fines. So this, from this literature, from this results, we can conclude that the Rajhara is not suitable to load as a raw material. As a lumps we can't charge into the blast furnace Rajhara, because it may generate fines, it will get a problem in the blast furnace, or during the transportation also it may generate more fines, because abrasion is more, means it will generate more fines, it will create more dust. So this ore is not suitable. So only thing how we can improve the strength of this type of Rajhara ore, means only thing option is in the form of sinter. We can increase the strength property in the form of centrifuges, we can do that one. So that is the alternative. So in our laboratory, the material tested, what the results are given, because here we can see shatter test of iron ore and limestone. Initial weight taken is 5 kg, 5 kg, and the weight fraction that is retained and plus 10 mm is 4.85, 4.75, and the shatter index what we are getting is 97% for iron ore and 95% for limestone. And tumbler test, we will get to two things we know, that is tumbler index and abrasion index. So here also iron ore and limestone we have taken, initial weights are 5 kilo, and on the two sieves we have plus 6.3, we got 4.75 for iron ore, and for limestone plus on 6.3 screen what we got 4.87. That is, this is the weight fraction on 6.3 mmc. And the material, the fraction of weight which the passed through the 0.5 mm screen means minus 0.5 mm. What is the weight we got from the screen is 0.05, 0.025. This will be the W3. So W1 is the initial sample weight, W2 is the weight fraction of plus 6.3 mm size, and W3 will be weight of 0.5 mm size in kg. So tumbler index will go W2 by W1 into 100, that is 95. Tumbler index we got 95 for iron ore and 97.4 for limestone. And abrasion index we can see this, how we will get the same thing, the 0.5 screen difference we will take W3 by W1 into 100, that is 1% we got for iron ore, and for limestone we got 0.5%.